Today I'm going to talk about the analysis of the very simplest transistor amplifier circuit. We have so far discussed metal oxide semiconductor field effect transistors as switching devices, as devices which are either in an on or an off state, can be modeled in the simplest terms as a switch. Today we'll talk about the use of a MOS transistor as a continuously adjustable valve, if you will. When vacuum tubes were first introduced early in the 20th century, the British tagged them with the label valve. It was not a usage that found its way into the United States very much, but it's a worthwhile usage because it illustrates in its common meaning the nature of the amplifying device. Think of a valve in a plumbing system where you can control the flow of water by opening it less or more. Think of a dimmer switch on an electric light circuit, where by turning the dimmer you are controlling the intensity of the light. The dimmer switch acts there as a valve. Basically, a valve, as we will think of it in electronic terms, is a device which controls the flow of power or of energy in an efficient way. Now, the MOS transistor, which we represent with this model, three-terminal device, one terminal called the drain, one terminal called the source, and one terminal called the gate. As a switch, of course, you control the flow of current between the drain and the source by controlling the gate to source voltage. We're more interested here in the complete characteristics of the device. And if we plot drain to source voltage and drain current, where this is the drain to source voltage and this is the drain current. If we plot those characteristics, we get a family of curves which look like this. For VGS less than the threshold voltage, and this is VGS. For VGS less than the threshold voltage, V sub T, there is no current flow. But then as VGS increases above threshold, one gets a family of curves which are non-linearly spaced and which look more or less like this, where this represents increasing VGS. Now, these curves are called parametric. They're a two-dimensional representation of a terminal pair relationship, namely the relationship at the drain to source terminals, but they are parametric in nature. That is, there's an infinite number of such curves that could be drawn. On each one, a particular value of VGS, of the gate to source voltage, defines that particular curve. As these are always represented with a few drawn, of course, but if you look at it on a curve tracer where you can shift the gate to source voltage continuously, you find simply that this is a curve which moves upward with increasing gate to source voltage, and depending on the increments you choose between these various values, you can have as many of those curves as you please. Now, the basic MOS, metal oxide semiconductor field effect transistor, MOSFET, and I should observe for the record that this is an N-channel device that determines the polarities of the voltages and currents. This is an N-channel transistor. If we put this device in an amplifying circuit, we will be able to analyze using graphical methods the behavior of that. Before I do that, let me just illustrate here and enlarge this a bit for you. The form of the characteristic curves of an actual transistor. This is drain to source voltage in volts, drain current I sub D in milliamperes, gate to source voltage in volts as the parameter. So this is a typical transistor characteristic curve. This is a curve tracer kind of representation of the sketch on the previous page. Now, if we put the transistor in an amplifier circuit, it looks like this. This is the simplest kind of transistor amplifier. It's called an inverting amplifier. A pair of input terminals there, and a pair of output terminals here, and a supply voltage up here, which I'll just represent as plus V sub S. What I mean by that symbolism is that the voltage drop from this terminal, power supply terminal, to ground, symbolized here, is V sub S volts. These terminals are where the input voltage is applied, and I'll describe that as little v sub capital I. And these terminals are where the output voltage appears, and I will describe that as little v sub capital O. I'm not trying here to be pedantic about upper and lower case, but we will find it essential as we move along in this subject to be careful about the use of subscripts and variables, because we need in the end 4 combinations of uppercase and lowercase, both on the variable and on the subscript. But this combination of lowercase variables with uppercase subscripts represent simply total variables. In other words, if you put a voltmeter on here and measured a voltage, what you would be measuring is V sub O. Now this circuit amplifies generally, because when I apply the input voltage here, once this input voltage V sub I gets above V threshold, that is, once V sub I is greater than the threshold voltage of the transistor, once it gets above the threshold voltage, current begins to flow in the drain to source channel. The current must be delivered by the power supply, flows through this resistor, which we'll refer to as the load resistor. And the voltage V sub O, which had been sitting up here at V sub S when this thing was not conducting, if I'm below threshold, there's no current flow in the drain to source circuit. Therefore, there's no current flow in the load resistor, no voltage drop across it, and V sub O must be up at V sub S. But as current begins to flow in the transistor, the voltage at this point begins to drop. And it is the behavior of that relationship, the relationship of the output voltage to the input voltage, that I want to explore today. This is an inverting amplifier. And as I say, about the simplest form of a transistor amplifier. The MOSFET is being used as a valve. It is controlling the flow of current in the drain to source circuit, and therefore controlling the output voltage. Now let's pull this circuit apart into 2 pieces. The transistor is one piece, and the remainder of the circuit is another piece, and see how we can work out a graphical solution. So here's the transistor by itself with the variables, current and voltage variables defined. If I draw the rest of the circuit by itself, it looks like this. R sub L, V sub S up here. This is, if I pull these out like this is the output voltage V sub O, and any current flow in this resistor is going to be the drain current when I connect these two pieces back together. Now, looked at this way, it's pretty clear how the analysis ought to go. The characteristic curves, which I showed you earlier, the characteristic curves relate the drain to source voltage and the drain current, two-dimensional relationship, with the gate to source voltage as a parameter. So those characteristic curves describe the device. That is, the characteristic curves of the device describe the device constraint. For any gate to source voltage, there's a particular current voltage relationship at these terminals, and that's the device constraint. Now, the remainder of the circuit involving the source and the load resistor can be thought of as imposing its own constraint. Specifically, the source voltage, the output voltage V sub O, and the drain current are related. Just applying Kirchhoff's voltage law and adding up voltage drops from ground to the source, the voltage source, we get V sub O, this voltage, plus the voltage drop across this resistor, which is I sub D times R sub L, had better equal the supply voltage, V sub S. Now, the fact that there's current here implies that there's something connected, as there will be when I put this back in place. But this relationship is the circuit constraint. This is the circuit constraint. The device constraint is the characteristic curves. The circuit constraint, KVL around this very simple circuit, is that. And now how do we put the two together? I should have said earlier, and let me make it clear now, that when I show a source voltage like this sort of hanging out by itself, there is always the implication that the circuit is closed back around to ground. In other words, somewhere out here in a manner that we don't care about, there's a voltage source, plus to minus V sub S. I should put the plus and minus signs inside, which is connected back down around to ground. The circuit is completed through the source, which provides this fixed voltage. Note that this circuit constraint is a linear relationship between V sub O and I sub D. Also, of course, V sub O, the output voltage, is just equal to VDS. That is, the circuit is constructed in such a way that the output voltage, as I've defined it here, is the drain to source voltage of the transistor. So this is an identity. Putting the two circuits back together then to the original amplifier gives us the complete amplifier. And to solve this problem, what we can do is take this linear relationship representing the device, the circuit constraint, and impose it on the nonlinear characteristics. On the nonlinear characteristics is commonly referred to as a load line. And while I'm illustrating it here in terms of a MOSFET amplifier, the concept of load line is extremely useful and comes into play whenever you're dealing with nonlinear elements. So what I'm going to do is plot the load line on the device characteristics, on the constraints of the device. I'll bring this up to make it larger here in a moment. But the load line, coming back here for a second, the load line has a linear relationship between VDS and I sub D. When I sub D equals 0, V 0 equals VDS is just V sub S. And when VDS is equal to 0, I sub D is V sub S over RL. So here is that constraint plotted on these characteristics. When I sub D is 0, the circuit constraint says that the output voltage, the drain to the source voltage, is just equal to V sub S, and that is that intercept on the curve, on the characteristics. When VDS equals V sub O is 0, X equals V sub O is 0, the circuit constraint says that the current is equal to V sub S over RL, and that is that point up on the current axis. Then I've simply drawn a straight line, linear relationship, the load line relationship between those two intercepts,